Perth Linux Users Group, talking Linux and open source.
Well, welcome to Plug's November talk. We're starting a bit late, so I hope everyone still has tuned in. Tonight we're going to have Stuart Midgley from Down Under Geosolutions talking about his experiences with Linux on large clusters. Without further ado, here's Stuart.
Hello everyone. It's been interesting watching the setup just tonight. It seems to be a reasonably common Linux experience. Not so long ago I had a rather nervous 48 hours where our petabyte file system wouldn't mount, and going in with a hex editor underneath the file system and adjusting bytes on a raw block device wasn't a lot of fun. Believe me, when you've got a petabyte of company data at stake. So glad it's up and running. So what I wanted to do tonight was, I was originally going to talk about what you have to do to get Linux running on large-scale clusters. And I'll talk a little bit about that, but also I thought I'd share with people some performance stuff that I've been doing lately, which has yielded some very, very interesting behaviour from Linux. And I thought that also might be entertaining. Slides are going to be quite minimal tonight. Anyone has any questions, feel free to ask. So, a little bit about us. We're a completely Linux house. We're a multinational company. We're 135-ish sort of people. Head office here in Perth. We're in KL, Houston, London, Singapore, Jakarta, Austin, and various places. And we basically run Linux everywhere. We run Linux on the desktop, we run Linux on our servers. We're an entirely Linux house. Unfortunately, it's not quite true. We occasionally have to run Windows for those recalcitrant admin people who seem to want to use Windows-based finance packages and HR packages and all that sort of rubbish. But apart from that, we're entirely Linux. So we use entirely Linux solutions. We're running OpenOffice tonight. Everything we do is basically Linux. At the moment, we're running mostly CentOS 6.3. We would love to have bought Red Hat, but Red Hat seem to have their head stuck in the sand, and when you start telling them you're running 25,000 CPUs, they don't seem to want to charge you just one price. They go, well, that's 25,000 times the single CPU seat, and becomes prohibitively expensive very quickly. So we run CentOS, and we basically support it ourselves. As I indicated, we've got a reasonably large system. Up until quite recently, we were the biggest machine in the country. We're running at about 1,000 nodes at the moment, about 25,000 cores. That's in a combination of compute nodes. We're running, our older systems are just 24 core, well 12 core, but hyper-threaded out to 24 core systems from Intel. Our most recent systems are the AMD Interlagos machines. So we're running 16 cores on a single chip and just 4 of those in a motherboard. So they're quite big machines. We're also now, our latest machines are 64 cores, 256 gigs of memory in a single box. So they're quite large systems, power hungry. As I said, we're running out, I think we might have gone over 25,000 cores. It's a bit hard to keep up with where we're at because we're just continually adding hardware. We're running, I think, my last count, or the count this morning, was we're running somewhere between 3 and 4 petabytes of online storage, which means a lot of disk. We're running that in a 110 node cluster file system. Again, all Linux based. So it's quite a moderate or big setup. As I said, until recently, with the machines coming online at the ANU in Canberra, we were by far the biggest machine around. And I suspect that give or take by the end of next year we'll be the biggest again. So we're growing at about 2,500 to 3,000 cores a month. So it's quite a rapid growth. And we buy stuff by the rack. So our base, and you'll see some photos a little later on, our base unit of buying stuff is one rack, 2,500 cores, and about 300 terabytes of storage. That's our other base unit that we sort of work in. And we just buy those every month to 6 weeks and just keep going. What do we do? We're a service company in the oil and gas industry. So we're doing seismic processing. Seismic processing is potentially the largest commercial use of computing in the world. Australia, across the world, there are millions of cores being thrown at seismic processing. And as I said, we were the largest machine in the country up until recently. As I said, we're running the latest machines we're buying are these AMD Interlagos. The model is 6276. If you don't know these are quite amazing chips. 16 cores on a die, 4 chips on a motherboard, so 64 cores on a motherboard. Interestingly, I put this in. There's 64 cores, but there are only 64 floating point units. If you know your architectures, the Intel chips have per core, like per real physical core, they run 2 floating point units. So in a 12-core system, you're running 24 floating point units. In these machines, you're actually running 64 cores, but a pair of cores shares a pair of floating point units. So it's sort of one per core, there's 1 floating point unit. Now, the interesting part about this is that if you buy an Intel chip, you get, if you buy the Xeons that we're running, there's 6 cores per chip, 2 chips on a motherboard. Right, so you're running 12 cores. Now, you turn hyperthreading on because our experience shows, but all the benchmarks show that hyperthreading gives you a little bit extra. The scheduling on the CPU gives you a little bit more. So you run effectively a 24-core node, looks like a 24-core node, and it's got 24 floating point units. It's also only got 24 integer units. These things, each core has got an integer unit. So you're actually running twice as many, even though you're not hyperthreading on this machine, you're not sharing any core facilities, you're not sharing any dispatch units, anything like that. You are only sharing floating point units. So whilst you're down on floating point units, you're actually up on everything else. And that's actually, for us, proven quite advantageous. It's given us quite a boost. The other thing about these units, you get an awful lot of memory bandwidth. Each chip's got 4 memory channels, and then you've got 4 chips on a motherboard, so you've actually got 16 memory channels on a motherboard. So they're quite entertaining. This is what I really want to talk about, I thought, after some stuff I did late last week. We went from CentOS 5.8 to CentOS 6.3, and all of a sudden our compute codes were going 40% faster on the AMDs, which was astounding. And I guess I hadn't appreciated just how complex these big 64-core boxes were. And this is purely down to the Linux kernel. The Linux kernel understanding the NUMA architecture of these chips. So you have, on a single chip, you have 16 cores, but they're in 8 groups of 2. So you have 2 cores. Each one's got a private level 1 cache. The 2 cores share floating point units and share level 2 cache. And then you have a level 3 cache sitting underneath all 8 pairs of CPUs on the chip. 5.8 kernel predates these chips, and so it knows nothing about their architecture. And I think it was just getting very bad memory placement and page placement. And so our memory bandwidth, we're probably striding right around the whole machine looking for memory. Whereas the new 6.3 kernel appears to understand the NUMA architecture, appears to get the page placement much better, and gave us a 40% increase in performance on the AMDs. Interestingly, the 6.3 kernel ran about 12% slower with the Intel chips, if on a single thread. Was faster if you ran all cores flat out. So you run a single thread, this kernel was slower on the Intels. But it was faster if you actually maxed out all your cores. So there seems to be some interesting interplay with the 6.3 kernel where it probably tries to lock processors and their memory placement much heavier. So it's actually much tightly bound on the CPU. So you're accessing much more nearline memory. Which means if you're running a single thread, you're actually down on memory bandwidth, because you're not using all the memory of all the other chips and everything on the system and all the other memory channels. But when you go to maxing out the CPUs, it performs much better. So that was quite interesting. It's really quite nice to get a 40% increase in performance. It's like buying another whole machine, another 20,000 cores or whatever it is. So that was quite amazing. So I strongly recommend, like I am at home, if you're running one of these chips, run the new kernels. It makes a massive difference. They are a fantastic CPU. I don't care. If you go, it's interesting. I can't understand where the mind of some people are at the moment. The AMDs, if you look at all the spec FP rate benchmarks, are faster than the Sandy Bridge, faster than any of the Intels, and yet they're not selling well. Our benchmarking performance now puts these miles in front of everything else, so it's quite amazing.
I believe the Intel marketing machine.
Well, I don't know. I mean, all that.
Intel's got a much better laptop.
Pardon?
Intel's much better on the laptop side.
Oh, maybe. I mean, these are quite a unique chip. I mean, I run one of these at home on my home server. It's quite nice. You can rip videos and things like that really quickly.
Yeah. How much does one of those set you back then?
Interestingly, we don't run the top bin because it's too expensive. But if you look at the mid bin, so 2.6 gigahertz Xeon, I think the last lot of pricing I had the Xeon, a 6-core Xeon, somewhere around $1,200–1,300. These are like 700, half the price. Greater performance, more cores, more everything. It's quite amazing.
How do they go on the single-threaded performance?
Now, faster, much faster.
Yeah.
I was quite surprised. As I said, the Intel slowed down and these things sped up. But our single CPU performance on a 2.3 gigahertz AMD is faster than the single thread performance running CentOS 5.8 with the Intels at 2.6. About 20% quicker. And about 10% less heat. And half the price. So for us it was quite compelling. It was really interesting. And I think we're about the only people in the country buying these things in bulk. So, quite interesting. That's sort of about the only informational 2 slides I have. What I thought I'd do is show you some pictures and talk about what we do with our Linux to make it work on these types of machines. I've already sort of indicated that we test which kernels and we benchmark our performance quite heavily. We also, because of the way we run things, we're quite concerned. Well, we've struggled actually to go to CentOS 6.3 a little bit. Really simple things just make life a little hard. They've changed a lot of the libraries and seem to have ditched some of the backward compatibility. So some of the binaries we've had compiled for 5 and 6 years stop working. So you've got to go back and you've got to go through everything and start recompiling and frigging around just because they sort of haven't provided backward compatible libraries. And sometimes we've just gone stuff it, we've just dumped the libraries into place. But I guess that's just the pain you suffer when you go through a major revision. So I thought I'd show you a screen dump, a snapshot I took on my iPhone this afternoon of one of our 64-core machines. These are in 1RU, right? So we have a 1RU 19-inch rack, but it's a 1RU, so 1 inch high system, right? 1, 2, 3, 4, 2.3 gigahertz CPUs. Hanging off those, you've got your 4. So this memory will be directly connected to that CPU, but this is actually, well, we've maxed them out with DIMMs, but these are, there'll be 4 memory channels there, 4 memory channels, 4 memory channels, 4 memory channels, and then what is it? Not hyper-threading, hyper-transport between all the CPUs, linking them up. As I said, the new kernel understands this architecture and runs heaps faster. So we use 1RU and we just buy 40 of them in a rack and stack them up. If you add up the energy, these are about 90 watts a pop, each of the CPUs. So you're looking at 360 watts just in the CPUs in these systems, multiplied by 40, you start cranking out the energy. DIMMs these days are sucking between 2 and 5 watts a DIMM. So again, by the time you've got 32 DIMMs in this thing, you're starting to build up the energy in the DIMMs as well. Of course, no system like this high density, you'll notice there are no CPU fans. All the fans are down here. So here are these bank of these 1-inch screamers sitting at the front. What this really means is that when you put your ear this side of the rack, it's bloody loud. It's so loud that our machine room is in quite a large concrete building with about this thick concrete ceiling to the offices above. When you go and stand above, you can hear these little things screaming away. So they're very loud. The nice things about modern CPUs, which Linux does really well, is control the speed. So when our systems aren't loaded, they crank down in gigahertz, which you probably don't appreciate on a system our size means saving of money. If we're using less power, we're obviously paying less cash. You might have seen an interview with our managing director on IT News recently where we're spending, I think it's about $30,000 a month on power. So I can't quite remember. And the carbon tax just added $3,000 to that. And having these things clocked down when they're not in use is critical importance for us. You know, if we're running a different type of workload, an IO-bound workload or whatever, it can make a significant difference. Having these things not running at 2.3 gigahertz, clocked down to 1.1, using a quarter of the power. So it's quite important. Again, we just have Linux. The other great thing, which unfortunately we've had to do, we control the speed of these things quite carefully in the case when a chiller fails. Our room goes from a nice balmy 22 degrees to about 70 degrees in the space of about 3.5 to 4 minutes when you don't have a chiller running. And when it's that hot, hypothetically speaking, you can't touch the buttons on the nodes. They're too hot with your fingers. So you have to use screwdrivers to turn your nodes off. Not a lot of fun, believe me. But yes, we now quite accurately control the gigahertz of these things. So if we have a system failure in the cooling systems, we clock them down very rapidly. Here's a rack. I just took a snap of one of our racks of these things. Dense. We're running, I think, about 30 kilowatts in a rack, which if you know anything about cooling a machine room, there isn't a machine room in Perth other than one we're in which really wants us in it. Most machine rooms are catering for the order of 2 kilowatts per square metre. So a rack takes about 3 square metres of a machine room. So they're catering for 6 kilowatts and we've got 30. So it adds up pretty quick. Other things which you may not appreciate, 40 machines in a 200 kilo rack adds up to about 1.3 tonnes. So these racks weigh in at 1.3 tonnes, add another 50 or 100 kilos with chilled water that we run through them, which I'll show a few slides later. So even just the racks themselves, are 1.5 tonnes with all the gear in them. So everything adds up really quickly. Here's a shot down one of the corridors. As you can see, just racks of compute gear. I'll show you some photos down the end of some storage we're running. Again, just think, I think we've got 12 of these big compute racks in this room, 13 maybe, I can't remember. Each one's 1.5 tons, and each one is generating 30 kilowatts of power. We're doing about 400 kilowatts, or close to half a megawatt. Next month will be a megawatt, half a megawatt sort of thing. That's what we're cranking through at the moment. Did I skip one? Go back. No, come on, open office. Here's a quick snapshot of some of our storage. Again, this is all Linux based. So what we're running here is a node with 12 disks in it, 12 3 terabyte SATAs, RAID 6. And then we just have 110 of these storage nodes in our clustered file system. 1.5 tons is light compared to the racks that hold these. Those disks are damn heavy. This is the rack we put this in. Actually, is an El Cheapo rack that we just hardened with a lot of extra support to keep the damn thing from buckling and falling apart. But yeah, I mean these little nodes, as a 12 3 terabyte SATA disks are pretty heavy. And then as I said, 110 of those floating around. So just some more. Well, so come on, go back. This is the front side of the rack. This is the back. Oh no, that's the front side as well. These racks, the servers are only half deep, so we run them back on the back side of the rack as well. So we don't have a hot cold aisle. We have cold cold, and we have a heat pipe down the middle to get rid of the heat out the top. Gigabit cables galore. Again, we run these and monitor these quite closely. We use a lot of our own custom written stuff and Nagios and bits and pieces like that to monitor temperature and simple things like on the RAID controllers, we monitor the batteries. You need to know when the battery's going flat and whether they need replacing, and the RAID card tells you all that sort of crap. So we monitor that, and when they're getting close to being replaced, we get new batteries and put them in, and etc. etc. It's quite an effort just managing this amount of gear. We're running, I don't think I've ever had the whole system up. just with a number of parts which fail and replacements are needed, and I think there's always been at least one node down. So you have to build systems to handle that. You going to give me the next slide? There we go. This is the back side of the rack, so you can see some splits up here. You can start to see the mess that is cabling. When you get to big systems, I'm a very, very, very strong advocate for no labelling on cables. Right? I've been in too many places where people label cables and they have too many faults. Because people go, oh, this is port blah, and this is the other one, and they just unplug it. And it's wrong, because a human put it in, and it was labelled incorrectly. I like to be able to take one end of the cable while it's plugged in, shuffle along the cable, and find out where the other end goes. So we purposely have no labels on our cables in our machinery. You have to follow every single cable to find out where it goes. Because otherwise you fall into this false sense of security that you can just unplug things. And then believe me, when you've got thousands of nodes, each with 5 cables in them, you've got 5,000 cables in your machinery, trying to track every single one and have a label management system and everything like that costs an enormous amount. And they are going to be mistakes. Whereas if you just follow the cable, you know where it goes. So, yeah, which of course causes a few dramas for some people who like neat and tidy machine rooms. Just an idea, I mean, this is a 48 port 10 gigabit switch. So this is supposed, they'll call this a non-blocking switch, which means it's got 480 gigabits backplane bandwidth, which of course is slight rubbish, but it's reasonably accurate. So it's quite a high-powered switch. This is our top switch, and then we run these 10 gigabit links out to all the other switches in the place. 1,000 nodes, 48 port switches. You do the maths, you have a lot of switches. Not only do we have the connectivity switches, these are all just Gig E at the moment, you also have your management switches. So you have remote management into everything. And so you've got a whole switching layer for interconnect, which is what this runs, this is the top part of. And then you have a whole interconnect layer for your management, so you can remotely power, get on the remote consoles of every single machine we have. So there's a lot of cables. This is the back of a node. We're running water-chilled racks, so these are like car radiators in the back. So about this thick car radiator with big fans on it, and we have cold chilled water running through these, so the heat comes out of the nodes and gets taken by the chilled water straight away before the air hits the machine room again. When you're running 30 kilowatts in a rack, this is about the only way you can cool it. You cannot physically move enough air to cool these machines. If you dump that energy straight into the air of the machine room, you would not have enough air cooling. You just can't do it. If you could, and it probably is possible, but it would be like a 50 knot breeze blowing around the place. Just enough. You've got to have the air movement. Air just does not have a high enough heat capacity to take the heat out. So we use chilled water.
So it chills in that and then blows out.
So the air comes out of the back of the rack hot.
Yep.
It gets blown through the back of the doors, and inside there's the chilled water radiator.
Does the air continue out?
And the air continues straight out of the rack into the room, but it's cool on the other side of the rack. Again, this is one of the reasons why machine rooms don't want us in them, because they don't have the capacity to take chilled water racks. I think we're about, not quite the only people in Perth running it, but we're pretty close. There's not a lot of them around. Very effective. Very, very effective. As I said, these things will take 35 kilowatts out if you have to. So, you can quite literally, if we didn't have LS storage, we wouldn't need air conditioning in the room. So it's quite impressive. Of course, then you have these pipes of water running around the bottom of your machine room, which of course makes a lot of people nervous. Water, computers. It's actually, we've never had a problem. Been doing this for 5 years, 6 years, and we never had a water leak. And the only time we get water in there is when we get a blockage and I'm jamming a screwdriver in to try and free the blockage, and then water pours out all over the floor when it gets released. That's about the only time we get water, but you know, everything handles a bit of water these days. So it's not really a problem. Some more, so of course you start getting lots of racks, you start having lots of these water pipes, and obviously our 32 amp 3-phase power down there as well, because we've had lots of, these are big power packs, they're about so big, and their cables are quite stiff, and the electricians came in and put them on all little posts all nice and neatly around the floor, but of course because everything was so stiff and couldn't move, I then went and unbolted everything from the floor and just had them floating loose in the bottom of the floor. Works really well now. Again, you know, little things when you're running these big systems and you're running chilled water, you've got these tiles, you're running 1.5 ton rack. Sometimes you've got to be careful where you cut the tile, because if you cut them in the wrong spot, they can start to bend and flex and potentially fall in. So sometimes it's easier just to not have a tile and just throw all your pipes straight into the floor. And then of course you have the fire suppression system. So if anyone, I mean, those cylinders are a bit tall for me, my head comes up to about here on these systems. So we have quite a large fire suppression system, so if anything goes wrong, a whole heap of gas gets dumped in the room. So hopefully put out a fire. But again, you know, it's a big room, lots of gear, lots of heat. You need large amounts of this gas. So it's quite an involved system getting this all up and running and going and reliable and no false alarms and all of that sort of stuff. But again, all of our monitoring, you know, and management of all this is done with Linux.
What gas is that?
I think this might be Fe200, which is basically just pure nitrogen. It has an extra little bit in it to help it clump. But yeah, I think it's just basically pure nitrogen and just suffocates the fire if anything happens. So just trying to you let the air in the room burn, and then there's no air in the room, and you keep the room pressurised with nitrogen so nothing else will flow in, and then the fire goes out pretty quick. So it's, I think that's this gas. There are all sorts of fancy gases these days. Some of them are actually react with the fire, the heat actually causes them to form little dust particles, which of course suck lots of heat out of the fire and put it out that way. This one, supposedly, if you're in the room when it goes off, you'll be all right. I'm not prepared to test it myself. But
It's not toxic, but you should not breathe.
well, oh yeah, don't lock the door on the way in. Leave it unlocked. Yeah, so as I said, it's quite involved keeping these systems up and running and going. Okay, back. Come on. I think I might have forgotten to take a snap of it, but I'll at least explain one part of it. Go back to the rack of stuff. So these are actually one of our AMD nodes. And so basically in one RU you've got 4 socket motherboards. Our Intel machines we're running actually, you have 2 nodes in one RU. So you have, there's sort of 2 blades in a 1 RU pizza box. And each one of those little blades has got 2 Intel Xeons on it. So they're the 2 6-cores. So we actually only go out in our Intels to a 12-core node, hyper-threaded out to 24, whereas these we're running 64 cores in 1 RU. So they're quite a lot more dense. Well, depending on how you count them. They've got more floating point units, which is sort of, for me, what's important. They've got more memory bandwidth, which is also important. And for us, a lot of our codes actually scale better the more memory we have under one node. So that's quite important. As I said, when you're running about 1,000 nodes, even the price of the operating system becomes significant, which is you know, another great thing about running Linux is it's free. We run nearly everything open source, even our clustered file system's an open source file system. So that's sort of quite good.
Which one is it?
Luster. So just all over GigE. It's quite entertaining having one file system, you know, 1.5 petabytes, 50 servers in it. When you have one server down and the whole file system's basically down. Just trying to keep everything up and monitor it carefully. We're running now, most of our gear stays up for a year plus at a time. These, the storage servers, we've gone really, we do things very differently. Most people who go into an IT house build SANs and have everything redundant. We've gone completely the other way. We don't even have redundant power supplies in our servers. One power supply. We have no add-on cards, so there are no NICs in, there's no PCI cards. The only PCI card in our storage nodes is the RAID card. And that is a direct attached SATA RAID card. There's no fibre channel, none of that sort of shenanigans, which one drives the price down, but gives us some flexibility too. If a node crashes, we just have spare nodes. And we just pull the disks out and bung them into another machine, turn it on, and we're back up inside 20 minutes. And then the technician can come in and do whatever he likes with the dead node for take as long as he likes, because we've got a number of these spare machines. For disk fails, of course, it's RAID 6, so you just pull the disk offline that node, so it gets no new data, so there's no writes going to it. There'll still be reads, but there's no writes. Let the RAID rebuild and we're away. We keep a stack of disks. So beginning of this year, with the floods in Thailand, I thankfully thought, all of these disk manufacturers have just gone offline. We quickly ran around Australia and bought 103 terabyte disks, which proved to be incredibly good judgment because we go through disks. We burn a disk every few days, fails. And when they were starting to take a couple of weeks to get replaced from the vendor, we were very pleased. We had a big stack of disks that we could just keep throwing in these machines and keep going. So yeah, we ended up with a lot of spare disks. As I said, rather than worrying about whether our vendor can support us and all that stuff, we just hot spare ourselves. Just keep the stuff on site. A couple of our staff, will drive in any time of day or night to replace a disk, keep a system up, keep it going. So it's a little different, I think, to a lot of your standard IT houses, which try to put all of the management and redundancy and fail-proofness into the actual hardware, and I think that's sort of fraught with danger myself. As an example, anyone here use UPSs? We don't have a single UPS in our machinery. I've had more problems from actual UPSs than I have power failures. So one site I was at, we had a big UPS. We had about a 500 kilowatt diesel generator connected to 500 kilowatts of batteries, so to speak. And the UPS wasn't even under load and the battery started burning. We couldn't get in the building for 3 days. So, I've had more failures of the UPS systems than the actual power. And, we just build our systems to handle power failures. If the system goes down for 20 minutes, that's fine by us. As long as we don't lose hardware and don't have problems bringing it back up, that's fine. So yeah, we don't run a single UPS in the machine room.
Do you have power conditioning?
Nope. We've got the world's biggest power conditioner sitting right there. The power supplies of these things have an enormous amount of capacitance. Even a brownout doesn't knock our system out. There's so much capacitance in our system just due to the number of power supplies we have that a power flip of less than a second, we don't even notice. So you just use the system as the big capacitor. So it's a little bit different. Saves a lot of cash. So, you had a question?
Oh, it was the same.
Oh, right. Yeah, so no, you just use the capacitance in the existing power supplies to buffer your system. These are, in every node's got a kilowatt or 1.2 kilowatt power supply in it. So add it up, it's quite a lot. The Intel nodes are, as I said, 2 nodes in one. One of the other things which people don't appreciate, and when I was talking to the AMD guys about this, because we got these chips before they were released and had one of these systems in, and one of the joys of this type of system is that there's half as many cables. Because the Intels, you've got 2 nodes in one OU. So this one's got 2 gig E's and a power supply, and this one's got 2 gig E's and a power supply. With these, you've got 1 OU and you've got a gig E, 2 gig E's and a power supply. So there's just physically less cabling. which of course means less failures. So we do see failures on our cables. I don't know if anyone else sees that, but we do have failures in our Gig E cables, and we even had, unfortunately, we had one of they have these big 32 amp power rails, right? So they're 3-phase 32 amp power rails, and these nodes, draw lots of power. So we were short a power cable one day. Didn't come with the machine or the rack, so we just grabbed an arbitrary one and bunged it in, and away we went. Problem is that the actual cable in it was thinner. Right, so it was 0.5 millimetre cable rather than 0.75. What that meant was that it was just marginally hotter. When you throw it at the back of a machine that's tossing out a bucket load of heat, the actual cable started to melt. The heat built up in it, and the plastic started dripping off the cable. So yes, we're now very, very careful about what cables we get. At the back of these nodes, it gets very hot. And really simple things can cause all sorts of problems. We had one power cable that actually got fused inside the socket. And so, we had to power it off and then get in there with a pocket knife and cut right around the socket and to get the power cable out before we could replace it. So, you can have all sorts of interesting problems. Yeah, it's the sorts of fun you have when you just have thousands of things plugged in. So, yes. The hardest thing knowing in this machine room is, how a lot of your hardware beeps when it has a failure? You don't hear it in this machine. So it's completely useless having anything which beeps in a machine room this size. And so it doesn't look much when you walk in, because it really is only 2 aisles. But it's just so dense, there's just so much gear that it's a little deceptive. Even our storage is more dense than... we're running each one of these racks. I think we run about a petabyte of storage in a rack. So, again, there's not too many systems which get you to that, and yet, we just build it ourselves out of commodity gear and Linux. We used to run software RAID, and I used to really, really love software RAID. One of the problems I've always found with hardware RAID solutions is if something goes wrong, you can't fix it. Right? You have double disk failure in a RAID 6, what do you do with a hardware RAID solution? Nothing. If you have a double disk failure with Linux, which I have had on a RAID 5 system, so the notion it's down, what you do is you just put the disk and you go, no, it's okay. You find out which actual blocks have got a problem. And you just DD them to 0 to force the drive to remap the blocks. So it'll remap on write. And then you just do an FSCK, and you might have lost a megabyte. And then you just very, very quickly get as much data off the disks as you can. And you can do that with Linux software RAID. You can't do it with a hardware RAID solution. There's no physical way to do it. So we used to run Linux software RAID, and it was really good, until we discovered that there's some really, really, really nasty failure modes for Linux software RAID. And they're very subtle, and they bite you at the worst possible time. And that is, modern drives have big caches, and they're getting bigger. And quite a lot of these drives nowadays will say the I/O has completed, even though it hasn't physically completed. It may not be entirely on the platter. Right? They can use capacitors to keep spinning post down, they can keep the stuff alive. And so sometimes it can return subtly too early. And then, a microsecond later, it throws an error to the Linux kernel saying, I couldn't write that, sorry. And the Linux kernel AMD device just happily ignored it. I don't know what that is from. It doesn't match any of my writes that I've just done. So it just ignores it. So you've actually got a failed disk in your system, and the AMD device just ignored it. And then you have a real failure, and then your RAID starts to try and rebuild. And then you hit the bit that was missing, that had a failure, and then you're stuffed. That's when you have to go in with a hex editor and DD and set the blocks to 0 to cause them to remap, so then the actual drive is happy. And then you can bring the RAID up, and then you just go hell for leather trying to get your data off before it all collapses in a heap. Having to do that, after I did that 3 times for 3 different systems, I thought, no, that's it. Hopefully these hardware RAID vendors track that sort of stuff, and so far, we haven't had a problem, so it's been quite good.
Any ideas which kernel versions you were using when you hit that delayed error system?
That would have been early CentOS 5, so 5.2, 5.3. but it's still there today.
So somewhere around 2.6.30, something around that, I imagine.
2.6.30? No, like 2.6.18. 2.6.
Oh, okay. Yeah, but that's a heavily patched Red Hat kernel.
Yeah,
so
that's
it might
right.
be more like 2.6.28 or something equivalent.
Very hard to know with Red Hat.
Yeah.
That's actually one of the things that's nice about CentOS 6.3 is that they seem to be doing much less actual patching of the kernel. So it's not as heavily, but they don't backport. They don't appear to backport as much as what they did in the CentOS, well, Red Hat 5 days. So, but yeah, it can be really tricky failure modes.
Ever thought of ZFS, or what are your thoughts on ZFS?
I'd love to run ZFS actually. I think ZFS would be really good. I don't believe it's in any state where you could really run it at the moment on Linux. And certainly our clustered file system, Lustre, you can't run on ZFS just yet. They are working on it, and there are ports which have it, but there's nothing really stable and proven yet with it happening. But yeah, I think ZFS would be great.
Yeah, it works okay on Linux, but it's not.
I'm led to believe the performance isn't great.
Depending on what options you enable. If you enable dedupe and compression, you just watch your go down. Works alright.
But yeah, no,
on read it's really good. On write it's pretty slow with the dedupe and compression.
Right. Yeah, I mean, we've sort of tuned our servers here. So we're basically run GigE. We don't do InfiniBand or any of that sort of stuff. And so with 12 disks, RAID 6, so you're technically only running 10 disks of theoretical bandwidth, and each disk can theoretically do, let's just say, 50 megabytes a second sustained, much less on seeking sort of workloads. So, from a node, you might expect to see 400 or 500 megabytes of I/O bandwidth. Well, it so happens that 2 GigEs will give you roughly 500 megabytes of total bandwidth, 400 megabytes of total bandwidth. So 200 reads, 200 writes. And that's sort of roughly what we see. If you've got the wind sailing and you're sailing in the right direction and you're doing large streaming IOs, we'll see 300-400 megabytes a second per IO node of bandwidth. And then multiply that by 100. That's sort of what we get. So it's quite impressive actually when you see your file system throwing out 20 gigabytes, not gigabits, gigabytes a second of bandwidth that you've just built on commodity gear. So yeah, we don't do a lot of tuning of the Linux kernel either actually. We find these days that the Linux kernel is mostly running pretty well. In the early days with Linux clusters, you had to fiddle around with time slices and stuff like that to get your codes running well, because the Linux kernel would too quickly use small time slices, but that all seems to be running pretty well nowadays. We boot all of our cluster is diskless. Well, a lot of them now have a disk in them, but we actually boot them diskless, so they just boot off the network, mount their root file system off our global storage, and just run completely diskless. So that's quite entertaining with Linux. It's reasonably easy to set up. There's lots of distros out there that do it, but we just rolled our own. I found that a lot of the distros and methods for booting clusters tend to be pretty heavyweight, whereas we wanted something pretty light and quick to deploy, so we just sort of quickly rolled our own.
Would you use as a base Linux from scratch or something else?
No, we basically, to build it, we just go and install a machine with CentOS, like a machine with disks, and then just rsync its operating system, and then build our own init RAM disk to boot the machine. So we just go and grab the kernel, whack it on, build a little init RAM disk that we throw it over TFTP, grab the kernel, build our own init script, and then once we've got the init script working, so it loads up the network drivers. So PXE, if anyone knows, what PXE does is basically a DHCP server with a TFTP client. So you tell it via the DHCP server, go here for the boot, download this kernel, and download this RAM disk. So the machine goes out, the network card goes out, gets those 3 files, brings them back in, and bootstraps the machine using that kernel and that init RAM disk. What it does then is, so you have a little init RAM disk that has your network drivers in it, a DHCP client in it, a few other bits and pieces, and use that to bootstrap up your base operating system. You then mount your network file system. Once you've got the network file system mounted, you can then do a chroot into your node image and then continue a standard Linux boot. So it works pretty easy. It's not overly complex. It's a bit of a bugger to debug sometimes when you stuff something up, but generally speaking, it's pretty easy. And all of the cluster distros out there are just various incarnations of that, and with various levels of complexity thrown on top. It's reasonably straightforward. You have to be careful of some things, like, I don't know if you go into / etc. There's this thing called mtab, which for no good reason it exists, right? Especially on Linux, where you have proc mounts, which mtab is the same as proc mounts. It's just a text file maintained by something else. Every time you mount, it goes into mtab. So, you know, we're on a read-only file system, so that doesn't work. So you have to symlink /proc /mounts into / etc / mtab. No biggie. Other things actually which people don't realise about Linux is you need a random number generator. Things like auto mount don't work without random number generators. Port map, which allocates ports in the ephemeral range, don't work without a random number generator. When you've got a node that has no USB devices attached to it and none of this other stuff, it's very hard to get entropy. So we actually roll our own Intel drivers, Intel NIC drivers, and we actually put a little syscall in the driver to go out and tickle the entropy every time there's a little bit of network traffic. So that's one of the tricks you have to do to get things working properly, or you have to find some other way to tickle and get entropy.
So the AMD chips don't have random number generators like the new Intel ones?
I don't know.
I think the Intel ones do have.
Yeah, right. Well, none of the Linux we've been running on the Intels uses it. So I don't know.
USB weather vanes, maybe?
It really is only 5 minutes to modify the Intel driver. It's quite literally just a couple of changes to an ioctal core, and away you go. You've then got beautiful entropy and bucket loads of it. So that's about the only two changes we make to Linux to get it booting off the network reliably and successfully. The rest of it's pretty straightforward. Just quite literally an rsync of a distro or a node install. So I don't have a lot more. I don't know if you have any more questions or you want to know any more about how we do it or what we do. We have some of the other tricks we pull. We use some various nodes of ours for remote access from various offices to other various, so we use VNC. But of course they're all headless. So we actually go and buy NVIDIA cards and whack them in it, and we don't actually want to attach monitors. And anyone who knows the NVIDIA world, if you don't have a monitor attached, it sort of doesn't work. It doesn't detect what size your monitors are and doesn't set up the display properly. So we sort of go in and hack around and trick the NVIDIA drivers into thinking there's some monitors attached and pull some tricks in the config file to actually set up external displays. And the reason we do that is, has anyone tried to use OpenGL applications via VNC? And no, it doesn't really work. If you just use a VNC server, it doesn't work. So we use this thing, which is just again another open source package called X11 VNC, which actually does screen grabs. So you actually need a true headed machine, which we don't have. So we dodgy that up. Then you run X11 VNC to actually go and do the screen captures off the NVIDIA card. And then you can do true OpenGL with any sort of performance. So you don't use Mesa or any of the software stuff. And that worked really well.
Why wouldn't you forward X over SSH?
Don't do OpenGL.
That's
Don't do OpenGL.
It's horrendous.
It's horrendous.
Yeah.
I'm curious.
Yeah, no, X over, I mean, I use X over SSH, but you don't use it for anything that's going to actually do 3D graphics or any performance stuff. The VNC protocol's heaps more efficient. So if you're prepared to put up with a slightly lossy compression, it does really well. So yeah, so that's sort of one of the other tricks we have to pull with our Linux systems. But again, you can do it with Linux. You're sort of stuffed under Windows or anything else. So yeah, we do a lot of remote work. And again, we don't use any of these proprietary solutions because we've found they all tend to be pretty poor. Just a really simple VNC setup. We've tuned our VNC parameters for our compression and decompression, and we know what our networks are, we know what our latencies are, so we can tune the buffer sizes and everything to get the maximum performance out of our VNC connections. So they work really well, even intercontinental. They're really quite good. So yeah.
Have you looked at any of the using any of the newer cloud systems to run your software like OpenStack?
We looked at it, and the biggest problem we have is that we have data. And it's very difficult to get a petabyte file system in the cloud, and very, very, very expensive. If you've ever looked at even Amazon Cloud and all these things, the data is what kills you. And a typical project for us is a couple of hundred Ts of active data. So it just hasn't ever really worked out. So, yep.
What sort of project planning lead times do you have on this sort of deployment? And what was your initial estimate and how different was it? We're a really bad company to ask. And the reason I say that is if the pictures of our setup don't indicate it to you, put it this way, one of these racks turned up from SGI, which is the vendor we use, 6:30 on a Friday night. And it was in and running by 3 AM Saturday morning in production. Me and another guy will just work 24, 48 hours straight to get the damn stuff in and running because we're desperate for the compute by the time it turns up. So I mean, we buy 2,500 cores and it takes 4 weeks to get to us. Like we'll quite literally go, right, we're short of CPU today, let's put an order for another 2,500 cores. That day we'll get a price from our vendor the same day that we want it, and then we'll order it, and then 4 weeks later it turns up, and then the day later it's in and running in production. That's the sort of time frame we go for. And if we could shorten it, that freight time, and this is Perth's a real pain in the backside to live in, right? Perth Airport can't accept air freight over 1.5 metres high. Can't get one of these racks in air freight. So what we do is the racks they've usually got sitting around. So we get those shipped early. So that the rack, which weighs a couple of hundred kilos, 2.5 metres or 2 and a bit metres tall, ships early, turns up, and then all the nodes get shipped as they get manufactured. And so what happens is we get the rack and we get it in place, and then we go hell for leather in the evening once the actual nodes turn up, racking and stacking and plugging in and redoing all the switching and pulling and plugging it all together and apart. And yeah, we'll get that up in 5 or 6 hours. So yeah, we move pretty quick. When we buy gear, we don't waste any time. We get new storage in, it turns up, it takes 3 days to sync the rate, so it takes 3 days to install. That's it. We don't go out, sometimes we go out around all the vendors and ask for pricing, and usually I say, all right, you've got 3 days to respond. If you don't get it to us in 3 days, then we will have ordered. And usually after about 2.5, 3 weeks, various large computer companies get back to you, and that they've just missed out on selling another couple of racks worth of gear. Whereas we've got a vendor which will turn it around in a day. So, yeah, it's quite different. We're a hard environment, and we're always desperate for the cycles. And but we're on this sort of, it's like everything in IT, order late, because it will have changed by the time you want it. So yeah, so we don't wait around, and our systems are set up for it as well. You get these nodes, you turn them on, they boot. That's it. There's not a lot more to it. They boot off the network, so you only have to plug them in and turn them on. So we have ways of automatically harvesting the MAC addresses, and that's all we need to set up the DHCP server. So we harvest the MAC addresses, it takes 10 minutes. And then you just power cycle them again, and they boot up, and then they're ready. So, and there's no better burn-in than just running your stuff on them in production. So we don't, there's no burn-in period or trial period or anything like that. We just get it in, get it running, and if something fails, well, we've always got something failed. So, having one more bit of gear fails is no real issue. It just takes a couple of days to get fixed. So yeah, so that's sort of how we run. So it's a bit different to a lot of IT installments. So.
One question over the way. What do you do? What's your...
Seismic processing. So
A little bit about our industry, because you probably don't know. At any given time, there's these big boats sailing the ocean, right? Big, really big boats. And behind them, they run huge amounts of gear. So they'll run these cables, which are 8 kilometres long, separated by about 150 metres, and they'll run 10 of those cables behind a boat. So you imagine you've got 1.5 k's wide of gear by 8 kilometres, and then they're setting off explosions in the water to detect the seismic response of the Earth in the cables. All of that data comes, well, not all of it, but we do projects which take that raw data off the boats and process it for oil and gas companies to help them find oil and gas. And so you'll get data off a boat, which might be, so a typical project startup might be 20 terabytes, comes in on tape in little plastic bags so that when they're dropped in the ocean, you don't destroy the tape. Right? So you might get 200 or 300 tapes in little plastic bags. Open up a little plastic bag, put tape in a tape drive, read the data. You know, a week later, you've read all the data off 300 tapes, and then you're ready to go with the project. And then, you know, we'll take 20 Ts and we'll blow it out to 200 Ts during the life of the project, and then spit back to the client, you know, 20, 40 Ts of data. So it's basically signal processing, but on a large scale. So we're running, if you missed the first time, we're running about 25,000 cores at the moment, 1,000 odd nodes.
If you're doing signal processing, wouldn't the Fourier transforms and stuff that you use run better on a GPU? Yes and no.
Single dimensional Fourier transforms don't actually go very well on a GPU. Multi-dimensional ones go better because you can parallelize over your other dimension. But also a lot of the stuff we do isn't just Fourier transforms. So we have a lot of other algorithms. Some are quite heavy on Fourier transforms, others are memory bandwidth heavy, some of them are flop heavy, depending on the process. But certainly we do use GPUs. We're just starting to come out with our first lot of codes which are done for GPUs now, and we'll be reasonably heavy down that road. But the problem I have with GPUs, you know, don't know if you kept up with it, right? You know, a couple of weeks ago the K10 was announced. Today the K20, or yesterday the K20. And we're running on K10s and they're quite good. Today, or yesterday, the new AMD S10000, whatever it is, came out, which is supposed to be 1.5 times faster than the NVIDIA's. Looks good. But you know, March, April next year, you're going to have the Xeon Phi come out, which is just a stock standard Intel architecture, but just 60 cores on a chip. So a very, you know, again, it's still a massively parallel chip, but you don't have to stuff around learning a new architecture or anything like that. You can use the standard Intel compilers and use some standard compiler directives to get in parallel. So it's a little difficult at the moment to know which way everything's going to go. Especially in the GPU market where it's so fragmented. You know, there are so many development environments, and CUDA doesn't run on the AMDs, and OpenCL runs all right on the AMDs, and to a greater or less, you know, depending on the features you want to use on the NVIDIAs. So it's quite complex and requires a lot of hand tuning. So yeah, it's a little bit of flux at the moment. But again, it's all accessible via Linux. If you really want a hot chip, get a K10. And the thing, I don't know if you've seen a K10. Oh, I wonder if I've got a picture somewhere. I've got a photo of what we had to do to get the K10 working. Let me just go back to the original, the start of the pictures, right? So here you've got, you know, a heatsink. It's only this high, right? Because it's in a 1-inch form factor. The K10 we put in these nodes. So you've got this 275 watt chip. These, remember, are 90 watts each. So you've got one K10 which is 275 watts.
Is it on a PCIe card?
It's on a PCIe card. So it sits sideways and it has no fans. Right? So we got one to play with, and we've got a desktop and we've gone, wonder how it gets cool. Well, it doesn't. So out comes duct tape and a big ass fan, and we duct taped the fan and built a little cardboard chute into the card, because the card's only this wide because it goes in 1 RU machines, right? And so we've got this fan about this big and built this little chute to feed it into the graphics card, and sticky taped it onto the graphics card and pumped air through the K10, and lo and behold, it now runs just fine. But they're relying on these little 1-inch screamers to get enough airflow through the node. So yeah, these graphics cards, 275 kilowatts, no heat, no fan. So yeah, very entertaining. But quite fast. 30–40% faster than your GTX 690 on single precision stuff, so yeah, they're quite impressive. No, you can't run graphics on it though. There's no actual DVI ports or anything on the back of it. It's just GPU. So, and they're quiet. Just hot.
So you look a big fan of
Yeah, well, yeah, that's why we went the big fan rather than the 1-inch screamers, because we wanted it sitting in with the developer rather than sitting in our machine room. So, because we didn't actually have a machine, we could plug it in the machine room. So, because obviously if you're going to plug it in, you can't have all of this stuff in the way because the card itself takes up the 1 RU height. So you can't have anything else. So you actually need a big slab of open space about this big to put them in. So you can't just go and buy a standard server motherboard and put it in 1 RU and expect it to work. So you've got to be a little careful. And we just didn't have one of those systems around, so away we went. Any other questions? No?
For the code that you do run on those, how's it compared to CPUs?
Our most recent benchmark, which is why I was playing around with Linux kernels, the GPU code on a single K10 GPU was about 1.5 times faster than our 64-core node. So when you consider a card has 2 GPUs on it and you can get up to 3 cards in 1 RU, you can get 6 GPUs in 1 RU, apparently. You can't cool it, but you can do it. Yeah, they're quite fast. So yeah, I mean, the system we're looking at would be 2 cards in 1 RU. So you're looking at 4 GPUs, so 8–9 times faster than a 64-core node, which is quite impressive. But we'll see. Quite expensive. A lot more expensive than a 64-core node. So.
All right, if there's no more questions, thanks Stuart for your fascinating presentation.
Thanks guys.
Thanks very much.
No problem.
Very interesting. It's fascinating to see just what can be done with Linux in such a large-scale deployment.
Yeah.
And water pipes running next to 32 amp.
Yes.
Well, yes, I hope everyone watching us live or on YouTube enjoyed that presentation. Next week, next fortnight, we'll have the next plug event, Plug in the Pub, Monday 26th of November at the Min and Sixpence. And then next month, December the 11th, second Tuesday, we'll have a talk from Adrian Woodley on IP version 6. I hope you can join us for that. Okay, thanks all.